Another geometry that we find the transient heat conduction, or we solve the heat diffusivity equation, is the solid when it extends from 0 to infinity, or what we call it semi-infinite solid. Which is when the solid extends from x0 to infinity, such as ground in contact air. As an example, let's say this is the ground, and the extent of this solid is infinity, and it starts, let's say, from x0 and then extends there. Assuming that the solid is initially at Ti, and so T of x and T initially at Ti everywhere inside the solid, and T equal to 0, then the heat flow would start if we change the surface condition. So the surface, let's say the temperature at x0, if it changed to another temperature which is different than Ti, then we would have a heat flux into the ground, or from the solid to the other medium that is in contact with that. Or let's say if we have a heat flux at the surface, we can have three cases here. We look at three cases based on the boundary conditions that we have. So in case one, let's say the solid surface temperature is suddenly changed to Ts. So let's assume this is the solid that we have. Everywhere is Ti, and then the boundary condition, T is changing the surface, Ts at x equal to 0 and T greater than 0, which this Ts is constant. So this is case one. This is Ti, and let's say the temperature just changed to Ts. The other case is when we have a flux. With some means we have a constant heat flux getting into the solid or going out from the solid. This is case two. Again, this is Ti, and here Q double prime is minus K dt dx at x equal to 0, and again assuming that's constant heat flux. And the third scenario is when we have this solid initially at Ti, case 3, and we have a convection happening. So there is a change of the environment that we have. Let's say initially it is at equilibrium with whatever fluid that is surrounding, and then we start like flowing some other fluids at the T infinity and H. Then we would have a convective heat transfer through the solid, and then conduction inside the solid. So the condition here would be minus K dt dx, that's the conduction. At x equal to 0 is going to be H T infinity minus T at the surface, x equal to 0. So this is a convection or convective boundary conditions. Now, if we look at the temperature profile at these three scenarios, we can qualitatively plot the temperature change inside the solid. So let's say this is X in depth of the system or the solid that we have in the semi-infinite solid, and this is temperature. For the first case, what we have is we are setting that one at a constant temperature. And let's say this is Ti. the initial solid temperature. So initially everything is at Ti. Now, the moment that we change the surface temperature to Ts, we have the heat transfer propagating inside the solid and then changing the temperature. So everywhere at the boundary condition, we have temperature. So this is increasing T, and this is for T equal to 0. The other case that we have a constant flux at the boundary, if the flux is constant, what does that mean is the slope of temperature gradient is going to be constant. So here, let's say everything is initially at Ti. Now what's going to happen is we have this flux that's getting in and changing the temperature. So if you look at the slope here, the slope is constant. As time goes by, so the slope everywhere at the x equal to 0 is constant. I'm just going to write it down. Constant slope, and the slope is dt dx, since we have a constant flux. This is the second one. And for the third one that we have convection, so let's say this is T and this is X. And initially everything is at Ti. So let's say this is temperature Ti. And now we are having fluid at T infinity. It could be the other way around, that the Ti is greater than T infinity, but let's look at that case at T infinity. So initially what's going to happen here, we're going to have the heat flux, the convective flux through the solid, and then heat is propagating inside the solid. As time goes by, we are going to have more and more heat transfer by convection and then conduction inside the solid. So this is rising time. And based on these boundary conditions, so these are the three boundary conditions that we have. So these are the boundary conditions. Initial conditions for all of them would be T is Ti at x greater than 0 and T 0. By having these two, we can find the solution. So solution for each case, solution to the diffusivity equation, to the 1D diffusivity equation for each case, we can find it as for case 1 is Tx and T minus T of S, Ti minus Ts. The solution here is going to be in the form of a function, what we call it error function, x over 2 square root of alpha t. So the solution is a function of x, location, and time, space, but this one is what we call error function. This is similar to log, but that's a function that you are less familiar to that. And we have tables to find out the value based on what we have in the parentheses here. And in general, error function is defined, let's say error function of x is 2 over square root of pi integral of 0 to x e to the power of minus u square du. And we can use table B2 to find out the values of error function. Now, if you evaluate flux is going to be upper prime at any time at x equal to 0 at the surface. This is going to be minus k dt dx at x equal to 0. So if you take the derivative of the above equations and do the math here, you're going to get k ts minus ti divided by square root of pi alpha t. And these are going to be in your text equation 560 and equation 561. This is for case 1 that we had a constant temperature. For case 2 that we have a constant flux. Case 1, constant temperature as a boundary condition. Case 2, constant flux. Then if you find the solution, it's going to be Tx and T minus Ti would be 2q double prime 0. This is the constant flux that we have. Alpha T divided by pi square, sorry, square root. Square root divided by k exponential of minus x square 4 alpha t minus 9x divided by k and error function c to the power minus 1 x over 2 of alpha t, where error function c is 1 minus error function for x. Again, you can use the tables for finding the error function. And similarly, this is equation 562. For case 3, where we have convection, convective heat transfer boundary condition, then solutions that you're going to find is Tx and T minus Ti, T infinity minus Ti. It's going to be function C square 2 square root of alpha T minus exponential of hx over k plus h square alpha t over k square x square root of alpha t plus h square root of alpha t divided by k. And this is equation 5.63 in your book.